Well, hi, I'm Cawen Xu from UC San Diego, and today I'm happy to present my work UnihanLM Coarse-to-Fine Chinese Japanese Language Model Pretraining with the Unihan Database. This work was done during my internship at Microsoft Research Asia. So let's start with the motivation. Traditional Chinese, simplified Chinese, and Japanese all share Chinese characters. However, their Unicodes are not always shared. So our motivation is we should find a way to exploit this ignored information and facilitate cross-lingual NLP. Due to historical reasons, Chinese characters have developed into different writing systems, including traditional and simplified Chinese and kanji. These characters with different Unicodes sometimes have identical or overlapping meanings. And the database we use here is called Unihan Database, which is a part of the Unicode standard. It's publicly available for everyone, and it is constructed by human experts. This database has more than 12,000 entries of variant information, and it constructs a graph structure. Um, the table shows five different kinds of variants in the Unicode Unihan database, and we only use the first four variants in our paper. We use the Unihan Find algorithm to find the maximal connected subgraph in the Unihan database, which is showed in the we show a example on the right. So it is a connected subgraph of Unihan database. For example, for the word typhoon, Tai is used in Japanese and simplified Chinese, while another character with a wind with feng on the left of the character is used in traditional Chinese. With these clusters, we are able to unify codings with Unihan. Here is a sentence example in Japanese, traditional Chinese, and simplified Chinese. It's the same sentence, but with the Unihan database, we can unify more characters instead of the originally merged characters with which is marked by a underline. So here is the workflow of our pre-training. We first use a coarse-grained cluster level pre-training. We merge characters to clusters and use cluster indices when doing cluster level pre-training. In this figure, #1 and #2 indicates indices of the clusters which Tai and the phone belong to, respectively. So it's like a masked language model objective, but we are trying to predict the classes instead of the original characters. And then we initialize the embedding of each character in the cluster by copying the cluster embedding. and we can then do a character level pre-training, which is basically the standard MLM to predict each character. So for more details of the pre-training, you can check out our paper. So we test the pre-trained model for different downstream tasks, and for word segmentation, um, you can see our UnihanLM outperforms the baselines with a large margin, especially on cross-lingual zero-shot transfer on this setting. And for the unsupervised machine translation, we have tested the performance of UnihanLM on the two different settings, and they both outperform the baseline. And notably, our UnihanLM even outperforms older supervised baseline open NMT, and it's kind of amazing. So for text classification, we test the performance of on a Pulse X dataset, and we outperform the XLM and multilingual BERT. We also conduct an ablation study. We first used a standard character-based language model, which is marked as minus cluster, and it has lower performance than our UnihanLM. And also we use the model after the first training phase, after the course level training phase. It's marked as minus character. We use that model to on the text classification task, and it performs worse than the UnihanLM. So it verifies the design choices of our model. So there are two takeaways. The first is linguistic resources can be helpful even in the era of BERT, and also the similarity between languages can be used for better cross-lingual NLP. For the code and pre-trained weights, you can access from our GitHub repo. And this is the end of the presentation, and thanks for your attention.